All right, so we're still in review land. These are things that we did last year. We're going to develop them further and feel more confident because they're not brand new. We're just going to see them and recall them and do them again. So 3.5 is called transformations of functions. We looked at parent functions earlier this week when we talked about all the different variations of x squared and x cubed, 1 over x, the square root, all of those. So we're going to talk again about them and call them the parent functions. That's what we graphed before. So that's the equation without any modification. And there we go. It's the most basic version of a function. Most basic version. So it hasn't been moved or moved left or right or up or down or stretched or shrunk or flipped over. So if you know what the parent function looks like, if you can pick that out, you can guess the shape and the domain and range from that. So if you know the basic parent functions, knowing the basic parent functions, if you know that, you can guess the shape, the domain, what x values are allowed, and then the range, what's going to happen with the y values. So let's take a look at the first thing that we really translated last year in Algebra 2. So that was this equation, y equals -3 absolute value of x plus 2 plus 7. So this was the modified version. The parent function is y equals the absolute value of x. That's the most basic version. And this one with the -3 in the front, the x plus 2 and the plus 7, these are all the things that have been moved around. So let's talk about these things. The parent function, again, is y equals the absolute value of x. That tells us that this is a v. And we know that because we know the basic shape for absolute value. We know that several different things happen. This minus in the front is outside of the parentheses, if you will, the absolute value bars. So the minus in the front tells us that it's not an up V. This one means it's flipped over. It's got vertical flip. And so this one's going to be a down V. That's kind of a crazy V, but there you go. The next thing moving left to right is the 3. And this is the vertical stretch. So the number on the outside moves things vertically. So this negative flipped it vertically, this stretches it vertically. It's going to make it a skinnier V. It actually, because this is 2 lines together, it has slope of positive and -3 instead of slope of positive or -1. Inside the absolute value bar, so inside the parentheses with x, this is opposite math. And it moves in the x direction, so left or right. This is opposite math. It says +2, which we think of +2 as moving this way, but it's opposite math. So it actually shifts it left 2. And then this number on the outside, again, outside, outside, outside. This number on the outside is the translation up. So this is a shift up 7. It's real math. It's not in parentheses. It's not opposite math. So what happens here? If I want to graph this, and I should not have put all that there. I'm going to move it down some. Sorry, my bad. I've got it up 7. So here we go. There we go. 1, 2, 3, 4, 5, 6, 7. So it's got an upshift. That means the vertex is at -2, opposite math, up 7. So up 7, -2. Here's the vertex. It's a V that has slope of positive or -3. So it's going to go 1, 2, 3 down, over 1, 1, 2, 3 down, over 1. That's this side. It's going to have the same shape on this side. And we have our V. Normally the parent function would have a slope of down 1 over 1. So it would be out this way. So when it gets stretched, it's actually a more skinny graph. So vertical stretch is like making it skinny. If you think about silly putty, if you stretch it out, it gets skinnier. That's what's going to happen whenever this number here is bigger than 1. So I'm going to talk about that right here. If we call this the A value. If A is greater than 1, it's a stretch. And if A is between 0 and 1, it's a shrink. So if it was 1/2, it would be a wider fat V, like that. Okay, so that's the one we did first last year. Let's look at some of the other functions that we know that we reviewed just the other day. So here we have our second example. It's going to be y equals x plus 2 cubed. So I want you to think about what this parent function would be and write that down. Think about what that looks like and jot that down. And then let's see how this would shift. So I'm talking about big ideas here, not an exact graph with every single dot in the right place. I'm talking about, can we sketch it and sketch it quickly with transformations? So the parent function for this would be y equals x cubed. It looks like this. This point was called a point of inflection. It's like half of the down parabola and half of the up parabola. It's called a point of inflection. This has been moved, and this is the shift. So the function here, so this is from the parent function. This is like the bubble in my mind that helps me figure out how to graph it. It is not at 0, 0 anymore. It's been shifted, and we write this as left 2. So instead of it being 0, 0, it's left 2. It has no plus anything, so it hasn't been shifted up. And it's going to go like this and then go down. So it's this kind of shape, but it goes like this. It's been shifted over to the left 2. If we did the same kind of thing with y equals the cube root of x minus 2. I'm going to graph this a little bit smaller. So this one has also been, I'm going to do the same problem. So plus 2. So we got plus 2. This has the same shift. This is going to go left 2. My parent function is y equals the cube root of x. It looks like this. It's sideways. And so now this 0, 0 point has been moved left 2, and I'm going to draw the same shape through that shift. And I could plug in other points to make this more exact, but for now I'm just trying to sketch the transformations. Now I have a little bit of space here. You might be able to squeeze this in. I'm going to do a different shift. I'm going to do y equals the cube root of x and put the plus 2 on the outside. So the plus 2 on the outside, this is like parentheses, and that has, I wrote the parentheses in there. This has 0 shift left and right. So this doesn't move anywhere left and right. But this number on the outside is real math, and it moves it vertically up 2. So I'm going to take the same shape that would be the parent function that would be like this, and I'm going to move it from 0, 0 up 2. And it's going to go like this. That's really like that. There. So up 2. And the 0 part doesn't change. So this is not a vertex per se. This is called a point of inflection, and that's a very calculus word. But it describes this change in the graph, this very specific point, which defines what this graph looks like and how it moved. Okay, we're going to keep doing translation so we can get really good at this. Let's do one with 1 over x. Okay, so this next example is y equals 1 over x plus 3. And this takes the 1 over x graph and it shifts the whole thing up 3. So let's look at that. Normally it's y equals 1 over x. This means up 3. The graph for this one normally looks like this. It normally looks like that, but our graph has been shifted up 3. 1, 2, 3. So instead of having this horizontal break right here, I'm going to have a horizontal break at 3, and now my actual graph tries to follow this dotted line instead of the x-axis, and the dotted line instead of the x-axis. So the whole thing has been shifted up 3. It's the same shape, just moved up 3. And sometimes it's helpful to sketch in the parent function and show your translation from there. Let's change to a different function. This function is going to be square root. So y equals the square root of x plus 4 plus 1. I have a number inside with x. That means it's going to be a left-right number right here. And this number is going to be on the outside, so an up-down number. This translation, and sometimes you have to write it in words. So this is going to be left 4 up 1. The parent function is y equals the square root of x. And it usually looks like this. It kind of goes up there. And ours that's been shifted is not starting at 0, 0 like the parent function. It's going to shift left 4, 1, 2, 3, 4, and up 1. So it starts right here, but it's going to have the same basic shape of the square root function. Now, what does that mean? That means the domain for this, you can look at the picture, it starts at -4 and includes it and goes to infinity. That's what my picture looks like. This is what we did with domain algebraically, and we've just sort of confirmed it with this picture. You could test other points, but if you're going to make an XY chart for the square root function, you want to pick numbers that are going to make perfect squares. For example, you might want to try 5. 5, because 5 plus 4 makes 9. The square root of 9 is a number I know. That's 3. 3 plus 1 is 4. So at 1, 2, 3, 4, 5, it's going to be at 1, 2, 3. My graph is not even that bad. So you could check to see if you're on the right trajectory for your values. But I do suggest you think in advance about what you want to put in your chart. You could put something like -3 in there. That would be square root of 1 is 1. 1 plus 1 is 2. -3 is 2. That's not so bad. I guess it's close to that. Okay, so thought process there. Let's look at flip. So we've got two different kind of flips. The square root of -x. The square root of -x has opposite domain. Normally the parent function has 0 to infinity. This has opposite domain. It's going to be -infinity to 0. It's been flipped. So this, because it's in parentheses with the x value, is left-right flip. because x is left, right. That means that if we graph this, and this is the plain Jane version, normally it goes from 0 and then 1, 1, and then 2, 3, 4, 2. Normally it goes like this, but this says we're going to flip it left, right, which means this value stays the same, but this value moves over here, and this value moves over here, and so it goes in the other direction. So when it's in parentheses with x, it's a left-right flip. And the domain for this is not 1, because -1 doesn't work. It's got to be all negative numbers because you're going to change them here. So the domain for this is also changed. The domain for this example is going to be negative infinity to 0, including 0. Okay, let's do that again, but let's change the negative to be on the outside. So negative on the outside means that if it's not in with x, it's not left, right, this is up, down flip. It's a flip in the y direction. So normally, and I'm going to draw the parent function again, normally the parent function goes like this. But we're going to take every x value we get out of our chart. Let's just do a chart. If we do it for the square root of x, if we put in 0, we get 0. 1, the square root of 1 is 1. 4, the square root of 4 is 2. But if we do negative the square root of x, every value we put in for x, we get the square root of 1 is 1, make it negative, negative 1. 0 stays the same. 4, square root of 4 is 2, make it negative, negative 2. So we go to these values, 0, 0, 1, negative 1, 4, negative 2, and it's flipped vertically. It went and flipped vertically. So the black line represents negative the square root of x. You can also, just because I have some room on this paper, you can do both flips. So let's do both. Y equals negative the square root of negative x. This flips it vertically. This flips it horizontally. And it looks like it was right here. It got flipped. It doesn't matter which one you do first. If you flip it vertically, it's going to be down here. And then you flip it horizontally, it's going to be here. So you can flip it in all kind of directions even at the same time. I'm going to talk a little bit about stretch again. So if I have y equals the square root of x over 10, what does that mean? That means that it's the same thing as 1/10 the square root of x. It means it's going to be the parent function, the square root of x, but it's going to be shrunk. This number is smaller than 1, so I'm going to know what the graph of square root of x looks like. We've just been graphing that. But this takes every x value and shrinks it. So this x value is going to be 1/10 of that. And this x value is going to be 1/10 of that. This x value is going to be 1/10 of that. And then 1/10 of that. So the whole graph is the same shape, but it's very flat because 1/10 is very little. So this would be the square root of x, and this would be 1/10 of that graph. And you could do it in an XY chart, and you might want to graph these things on a calculator to do them quickly. You can compare a lot of numbers and see what happens there. So again, if this value is, we call it the A value, the stretch value, if it's between 0 and 1, it's going to, like this one, it's going to be a shrink vertically. If it was a bigger number, so if we had a pink graph on here, y equals 2, the square root of x, it would take every value and double it. So this value is this far, I'm going to go and double it. This value is this far, I'm going to double it. So it is double the graph to the square root of x. So this would be a greater than 1, and it is vertical stretch. So these are all notes that are reviewed from last year. Hopefully they are making some sense to you. You should be able to pick them out. It doesn't matter what kind of function it is. All of the different stretch and shrink and shift values apply to polynomial functions, radical functions, and the rational ones like the 1 over x. The new thing that I want to talk about is even or odd functions. It's not brand new. We talked about it a little bit last year, but this year it's actually important and you'll need to know it and memorize these ideas. So this is the section on even and odd functions and what that means. So a lot of it comes from just the idea of it being even or odd. But I want to show you what it looks like. It's with respect to the origin specifically. So this is with respect to the origin. So you can't have things shift left or right and still be even or odd. So this is what I want to talk to you about, and that is looking at even functions first. The first one that you might think of as being an even function is the plain Jane y equals x squared. It's an even function because whatever happens on the left also happens on the right. So it's like a mirror image. Whatever happens at x is greater than 0, so this is whatever happens is like our y value, at x equals 0 also happens at x is less than 0. So it's a mirror image at the y-axis. The y-axis looks like a mirror on either side. So you know what y equals x squared looks like. It's a parabola. When I draw them good, they look the same on either side. If I go to any x value, like let's say 1. If I go to 1, my y value is also 1 for this one. So I have the point 1, 1. If I go to negative 1, my y value here is negative 1 squared is also 1. Pretend that my graph is perfect. I'll pretend and put it here. 1. There we go. So at negative 1, I get the same y value. The same would be true for 2. At 2, we would get 4. 2 squared is 4. And at negative 2, we would put it here. Negative 2 times negative 2 is also positive 4. So whichever x value, as long as you put it in positive and negative and get the same y value out, it's an even function. And that happens, it's called even because this is an even exponent. And it comes from there. But here's the math that makes us understand that, or is a proof. How do you prove this? So how do you prove this? You prove it just like this idea of 1 being positive or negative and giving the same y value. You test it with function notation. So if you plug in a negative value for x and you get the same value out. So if I plug in 1 and get 1, and I plug in the negative value, negative 1, and I still get 1, then this is an even function. Let's test it with some stuff. Let's test it with this one just because it's here. Y equals x squared. We're going to test it with this notation. So I'm going to plug in negative x into x squared. So this is x squared, something squared. I'm going to plug in negative x. And I already know that the function value equals x squared. And you ask yourself, is this a true statement or not? That's a short version of statement. And it's true, because negative x times negative x is x squared. So this is even. And it works for a lot of different functions. In fact, let's try another one. Let's try example 2. So we're going to call this one, we'll just call it f of x equals 3x squared plus 1. Now you might be able to graph it and know what it looks like. It is an even function, and I'll show you what it looks like in just a second. But how do we prove it mathematically without a graph? So what we're going to do is we're going to see if we plug in negative x, if we rewrite this function and we plug in negative x, remember function notation means that we can take what's written up there, the 3x squared plus 1, instead of putting x here, we're going to put negative x here. So here we go, negative x squared. Now they look the same, 3x squared plus 1, 3 input negative x squared plus 1. Do the math out, and we have 3 times negative x plus 1. That's 3 times x squared plus 1. This is equal to this. I plugged in negative x, and I got the same thing out. So this is, yes, this is an even function. And I told you translations weren't allowed, but that's left-right translation. This is an up translation. So this starts at positive 1, and it grows pretty quickly, so it's skinny. But if I drew it, perfect, then this side would equal this side. At every x value, I would get a y out. And at the same value on the negative side, I have the same y value. Even function. You need to memorize this rule right here. F of negative x equals f of x. That's how you prove something is even. We also know what an odd function looks like because we know what x cubed looks like, and it's called an odd function. There's another name for it that we'll talk about too, but odd function is the easiest way to think of it. So let's look at odd functions. So f of x equals x cubed. That's the easiest odd function to think about. I mean, a line would be easy, but that's really boring. So this is an odd function. The parent function looks like this, where we're up here, and then we hit 0, and then we go down here. Now, odd is different than even. If I go to an x value here, I get this y value. Obviously, if I go to the same x value, so this far away over here, negative x, I get a different y value. So this is one y value, and this is a different y value. This is actually the negative y value. So unlike even functions, you don't get the same y value out. You get the same number, but it's the opposite sign. So here's the how to prove it for odd functions. If f of negative x equals the opposite, so negative in the front of the function, then it's an odd function. Let's try it with this easy one. So I'm telling you that f of x equals x cubed. What would happen if I plugged in negative x? So I'm going to test it. I'm going to say f of negative x, and I'm going to write the function cubed, because that's what I'm given up here. X cubed. Something, a variable, cubed. The test says plug in negative x. So I put negative x right here, and that means negative x times negative x times negative x, and that is equal to negative times negative times negative is negative, x times x times x is x cubed, and this is negative on the outside, the function. I was given x cubed, and I have a negative in the front. That makes this an odd function. It's also called symmetric with respect to the origin. On the even one, you can think of it as a mirror image. The y-axis is like where you would fold a piece of paper, and these functions would be the same on either side. An x cubed graph, you'd have to fold it and then fold it again for it to be symmetric that way. So odd functions are also called symmetric to the origin. It's like you have to fold it twice. So let's look at another one of these guys. Let's say we have f of x equals negative 2 x cubed plus x. So there's my function. Is it even or odd? Or is it neither? Most functions are neither. Most functions do not go through the origin. So it's entirely possible that it's neither one. But let's test and see if it is either one. So what I'm going to do, the test is always plug in negative x. The result tells you whether it's even, odd, or neither. My function says negative 2 times x cubed plus x. Negative 2 parentheses cubed plus parentheses. Those are my input values, the parentheses. I'm going to plug in negative x. Negative x, that's the test. I'm going to work out the math and see what I get. I have negative 2, negative x times itself 3 times is going to be negative x cubed. It stays negative. Minus x. This simplified is negative 2 times negative. That's going to be positive 2x cubed minus x. So here's the question. Does this equal negative f of x? You want it to look just like negative f of x to be able to tell. Right now, f of x says negative 2x squared plus x. This doesn't look like that. If it looked exactly like this, it would be even. So it's not exactly like it because it has the wrong sign here and the wrong sign here. What if I take out a negative so I can put it in this form? If I take out a negative, it would have to be negative 2x cubed. Negative times negative, it would have to be positive x. And yes, this one is odd. Yes, this is odd. Because it looks like negative, and this is what I'm giving up here. So I have negative the function value right here. So this is an odd function. Even and odd are important because if you can graph half of it and then know how it reflects on the other side, then you can easily draw it out. So for example, if I know that sine, and we're going to do this soon, if I know that sine is an odd function, just as an example, if that's all I know about it, and then I also know that sine starts at the origin and does this thing where it goes up and down and up and down. If I know it's an odd function, then I can predict that on the other side, it's for every x value that's up here, the same x value is going to be here. It's going to go down. So this is a positive y. This is going to be the negative y. Odd returns the opposite y value. So it's going to go down where this goes up, this one goes down, and it's going to have some sort of not a maximum but a minimum. Then it's going to go down, which means it goes up. It does the opposite, and I have a sine wave. So odd and even describe things very cleanly and precisely, and your test is to plug in negative x. Write that down. That is how you tell one or the other. Okay, so you've got some practice like this, odd or even, and you've got transformations of functions. If you're having trouble with this, I need to know. And otherwise, we're going to move on through because these are things you've seen before, and we're just putting it all together so that we know more about algebra before we move on to the trig stuff, which is like sine and cosine. So we're going to cover all of the polynomial things, rational things, and exponential logarithms before we move to the trig functions. And that's what we have for today. Thanks.